Hi, in this video I'll be presenting L0-Sampler, an L0 model-guided volume sampling for NeRF. First, let's review the Neural Radiance Field, or NeRF. It synthesizes novel views from plenty of multi-view images. It samples points along camera rays and renders pixels through volume rendering. It uses a MLP to output RGB colors and volume densities based on positional data and ray direction. When deciding where to sample along each ray, NeRF employs a coarse-to-fine strategy called hierarchical volume sampling, HVS. It starts with uniformly sampled points along the ray. Using these, it generates a piecewise constant color weight function, WT, and normalizes this as a PDF to guide further sampling. However, real-world rendering often demands more precision, focusing sampling precisely on the surface. To better represent the characteristics of real-world WT, let's revisit the L0 distance concept. The L0 distance is induced by the L0 norm. It determines whether a point belongs to a set. Applying this to NeRF, if we consider the surface as the set, 1 minus the L0 distance will sharply change as points intersect with the surface, resembling the real-world WT. We term this similarity the L0 property of WT. Our purpose is to incorporate the L0 property into WT to enhance sampling efficiency and focus. The challenge is that during training, the exact surface location is unknown. To overcome this, we employ piecewise interpolation to achieve a quasi-L0 WT, thus balancing the optimization of residual space and maintaining the L0 property. We start by transforming each interval into a unit interval and then interpolate within these. The transform W hat(S) is designed to approximate a steep indicator function. Our research has identified two practical base functions, the piecewise exponential and the piecewise inverse functions. They adaptively shift shapes, becoming steep when endpoint weights differ significantly, directing sampling points towards interval ends. Our method follows a straightforward pipeline. Starting with uniform sampling as in NeRF's coarse stage, we then apply our quasi-L0 WT through piecewise interpolation. After normalization, this serves as a PDF to guide inverse transform sampling, concentrating sampling near the surface, as our sampling frequency visualization shows. Implementing our method from NeRF's HVS requires only a few code adjustments, approximately 10 lines. Each step, from normalization to inverse transform sampling, has a closed-form solution, avoiding extra computational load. This video demonstrates a comparative analysis between traditional NeRF and our L0-Sampler enhanced NeRF. To better show the comparison, we show the PDF of a ray using piecewise inverse functions without max blur, and on the right are the RGB figures of rendering of the complete model. Notice how our method results in more focused sampling and improved rendering, especially visible in the RGB figures. We add our L0 sampler to different NeRF frameworks using importance sampling and test them. Results show that models using our extension consistently outperformed the baselines in PSNR. Here are the rendering results of NeRF in the Blender dataset. Our sampler helps to capture challenging details, like highlights, complex textures, and thin structures. The test on the LF dataset by NeRF++ shows that our L0 sampler can also improve the rendering of more complex scenes. In addition, in sparser sampling scenes, our L0 sampler can capture better details of geometry. Furthermore, the quasi-L0 WT improves geometric detail capture, which is crucial for techniques like Noose in 3D reconstruction. Our sampler's integration with Noose can improve geometric results, including capturing more geometric details and correcting unnatural shading effects. Thank you for your attention to this presentation.